Hi everybody, welcome to Mrs. John's class. This is primarily for Year 13 Physics. This is lesson 4 on DC and capacitors, and today we are looking at a little bit more about internal resistance and what happens when cells are discharging or charging. So when a cell is new, the chemicals are all fresh, it has a very low internal resistance, and so it can supply a lot of current to the whatever it's discharging to. And so we have the EMF of the cell, which is always greater than the terminal voltage. So the equation that you use when a cell is supplying energy, we say that it is discharging, and when it does that, the equation that we use is EMF is equal to terminal voltage plus the voltage drop across the internal resistance. Now over here, your terminal voltage V is equal to I times R, which is the circuit current times the resistance. So let me just label this diagram. So this is the EMF of the cell, this is your internal resistance, this is your external load. Now when a cell is discharging, the way that the current flows is out of the positive into the negative. So current flows from this way through the battery. Okay. Now over a period of time, the chemicals gets used up and chemical reactions take place, and so the internal resistance of a cell that is old goes up, and so it cannot supply enough energy to the external circuit. So if you try lighting a lamp using an old cell, it's going to be dim or not glow at all. Now cells that can be recharged can actually be charged up. So that's called charging a cell that's been flat. Like for example, when your car doesn't start and your battery is old, you call AA, or you call a friend and you kind of jumpstart the car. And in order to jumpstart the car, you're taking some energy from a good battery and supplying it to your old flat battery. And in order to do that, you've got leads. Now the way that you connect the leads when you are charging a flat cell, you need to be really careful, because in this case the positive is connected to the positive and the negative to the negative. And the new cell will always be at a higher potential, the charger. So I've got a second diagram here. This is your flat cell, okay, which needs to be charged up. It's connected to a charger. Now the charger is always at a higher potential. The reason is current can only flow when there is a potential difference, and it flows from higher potential to lower potential. So when a cell is being charged, the way that the current flows is out of the positive terminal of the charger into the positive terminal of your flat cell. So do you notice the direction of the current through the flat cell is opposite to what it would be if the cell was discharging, or in other words, providing energy to some sort of load. Okay. Now the thing is, initially the current is going to be very high because there's a lot of potential difference between the good cell and the flat cell. Okay, so but as the flat cell gets charged, the potential difference decreases, and your current, the rate of flow of current, is going to slow down, and it'll stop once your flat cell is fully charged and there's no more any potential difference. Now this is the only case where the EMF of the flat cell is going to be lower than the terminal voltage. So the equation that you use is a bit different from this one. The equation that you're going to use is the EMF is terminal voltage minus internal resistance. This is for when a cell is being charged. If you want to rearrange this equation, you can get EMF plus the voltage across the internal resistance is equal to the terminal voltage. There is a question in your booklets where it has this sort of a question where the cell is being charged. So when you're solving problems on internal resistance, it's quite important you read the question properly to find out if it's a question where a cell is supplying energy, or is it a question where a cell is flat and the cell is being charged. Hope that helps. Bye for now.